Well, after the steel cable stayed bridges, we come to the next type, which historically became important. We come to the concrete cable stayed bridges. When I speak of steel concrete cable stayed bridges, I always mean the material of the beam. Both types can either have concrete towers or steel towers. So, just for simplification, why concrete cable stayed bridges? Well, the reason always is they are sometimes more economic. That's what the name of the game. We want to win the competition. So, why is that so? The beam of a cable stayed bridge is very heavily under compression from the inclined stay cables. Now, concrete loves compression, whereas in steel we have to strengthen it against buckling and all sorts of things. And it is clearly less expensive to carry a compression force in concrete than in steel. Very roughly speaking, if we have a column in steel and concrete costs certainly not more than about 2/3, if possible, in concrete. Sometimes it doesn't work. So, in addition, the heavier weight of the concrete means stronger cables. That is, for the same life load, we then have less of a fatigue range, and aerodynamic stability is higher, just because the thing is more heavy. The shortcoming, of course, is because it's more heavy, we need more cable steel. So there is a trade-off between less costs for the beam proper. A concrete beam is less expensive than a steel beam. However, we need more money for the additional cable steel. And that turns out, roughly, that for the shorter spans, say 200 to 400 meters, very often a concrete cable stayed bridge is more economic than, say, 400 to 700 meters. It's a composite beam, meaning a steel grid with a concrete deck. And for the very large spans today, it's steel. This is very rough. It depends on the country and what the contractors know and world market conditions are. You can't really foretell. But that's very roughly. The shorter spans are very often more economic in concrete. The very long spans are economic in steel. And in between, we have the mix, steel stay girder grid, and concrete slab on top, meaning composite. So, now, we now come to the development as we had in steel. We make it historically. The very first one, for a long time, unknown, at least in Germany or in the books, was the Belajar bridge in France across a lock, ein Staudamm. And it was designed by a famous French engineer, Albert Cacot. But he wasn't a famous bridge engineer, because this was, to the best of my knowledge, the only bridge he's ever done. He was a hydraulic structure engineer, dams and locks and things like that. But here he had the necessity to build a bridge across one of his hydraulic structures, and he sat down and thought about it and made it all right. So this is the first cable-stayed concrete bridge. It has a trough cross-section. The stay cables are stressed, you can see here, to the predetermined value. They are anchored correctly to the beam. It is the first concrete cable-stayed bridge. built by a hydraulics engineer. Just rational thinking. Now, it then started in earnest in Germany with the Main River Bridge at the chemical plant of the company Höchst near Frankfurt. And the situation was a little special. There was a very short side span. Finsterwalder, who was the engineer, designed it in parallel, and then he had too long a main span, so he instituted here sort of a sail which grows out of the beam to increase the construction depth there. It's called a concrete sail. I've done it later, we'll see with the East Huntington Bridge the same, but we placed a haunch underneath the beam to take it over there. And here then the railway line had to go over plus traffic lines, so the railway runs between the two tower legs, and he then, Finsterwalder then designed the two in harp shape, balanced, and used for the first time what he also had invented, Dividac stress bars for the stay cables, not the ropes or wires or strands, but bars, you know, the stress bars from Dividac. Within a thick steel pipe, we will see about all that in a special lecture on stay cables. So the first mainstream, if I say the Donzière, is an exception, just once, one shot by a very talented engineer, but not a bridge engineer. Finsterwalder, however, was also a bridge engineer, and he went on. So this is normally considered the start. Finsterwalder, one of the top engineers in Germany, especially after World War II. Finsterwalder in concrete, Homburg mainly in steel, Leonhard more concrete. I would say those were the three independent consulting engineers. There were, of course, important structural professors and so on, but the consultants, those were the three. Finsterwalder as a working for the contractor, being the chief engineer for the contractor Dückhoff and Wittmann, and Leonhard and Homburg as independent consultants. The next one, Paraná Bridge, I mentioned it, Sarate Brasilargo. There's another one, Chaco Corrientes. We have to mention it for historical reasons, but it's very similar as Morandi's Lake Maracaibo Bridge. So it's not, I'm not going very much into that. We will talk later about Morandi. A new one, Danube Canal Bridge in Vienna, die Donau-Kanalbrücke in Wien. Special insofar by its construction methods. The situation was such that it was most economic to build the two bridge halves parallel to the canal on both sides, and then turn the thing in. So it's construction by rotation. That makes it quite unusual. There's another one, Ben Ahin, which we will see later in Belgium. Now, most famous concrete, I would say, yes, concrete bridge professor and engineer in Vienna, Professor Pauser, was the engineer for that. He was kind enough to write a book review on my book on cable stayed bridges. So, then came Pesco-Kennewick, which was the first where I was really on my own. Leonhard sent me alone to the United States for detailed design and construction engineering, everything, and I hadn't in that way done it before. So it wasn't simple, but after I was through with that, I said, well, nothing worse can happen to me, and that was a fact. 300 meters, 299, it's 1,000 something feet. The first one from precast elements, and we will have a special lecture on that. I just mentioned that 270-ton precast elements. The biggest we had match cast, epoxy glued, parallel wire, cable stayed bridges, all special things, and as I said, for a long time the world record, until the Breton was a little bit quicker, and they were a few months ahead with 320 meters. Well, if you pull, it's still the world record with precast elements or something, but it never had it. After that, across the Ohio River, I did the East Huntington Bridge. Somehow similar precast elements, but we had an A-tower here, and we used floating crane. There we had a derrick on the deck. And here we had the same situation. Well, we had problems with the foundations, that we said, okay, we want to take as much as weight as possible here to this side. And so we built here, had a haunch in, built this free cantilever, and on all the weight of the concrete here goes back here, and only this part has to be tied back. Is in its way also a world record, 274 meters times 2, 550 in concrete precast elements, but it's an important bridge. I show the Sancho el Mayor in Spain as an example for many outstanding bridges in Spain. The Spanish engineers have a knack for, I say, designing beautiful bridges. If you look at it, I mean, the tower really is developed. And in addition, they have the craftsmen, the artisans on site to build these involved shapes. I'm not sure whether we could do it in Germany. At least people would say, much too expensive, no way. But in Spain, they do it. And so if you're there, look at them or look at pictures. They have outstanding bridges. I admire that. I'm not the one to do it. Mine are always straightforward and economic. But I admire these people who can do more artistic shapes, and that's just one example. Again, across the Paraná, where I think we've done by now 5 cable-stayed bridges in Argentina. Posadas Encarnación, this time in concrete, also with a railway, eccentric railway line. We will see about that later in some detail. Then came Helgeland, the most daring bridge I've ever designed. 425 meters in Norway. It's in Norway at the polar circle, 20 kilometers away from the polar circle, at the west coast of Norway. And the problem there is not temperature. It's not colder than here. The Gulf Stream is still active there, but extremely strong storms, especially during winter. 250 kilometers per hour wind, and it took place several times. We'll have a special lecture on that. But with the 425 meters, which was required because the fjord is about 120 meters deep, and we are only 1.2 meters high, that's 1 in 355 slenderness. Free cantilevering with very heavy storms. Dr. Kovac, my aerodynamic specialist, he calculated it and said, well, we had to believe him, and he was right. But it was the most daring bridge. I think one of the most daring cable-stayed bridges due to the circumstances there are. We'll have a special lecture on that. Unique other cable-stayed bridge in Norway, Solhus. It's the only cable-stayed bridge in the world which connects a floating bridge to the mainland. This is a floating bridge because the fjord is several hundred meters deep. You cannot good found. So it's floating caissons from lightweight concrete on which it sits. And now we need a navigation channel which we cannot have here. So this cable-stayed bridge is connected to a floating bridge. The only one, I think, in the world. There are a few floating bridges, Lake Washington in the state of, near Seattle. There are some, but very few. Lever River Bridge in Scotland is special in so far in two ways. It's only reinforced, no post-tensioning in. That means we have cracking of concrete under life load, which means, because most of that is restraint moments, we have a reduction of elastic moments due to plasticity, which helps. And on the contractor decided to build the complete bridge on one big long scaffolding, which we thought, well, he does it in pieces or free cantilever and what. No, so that's okay. We'll see it later under construction. One big piece of structure underneath, timber, over the full length. I don't know how he could make that economic, but that's what his decision. Rosario Victoria, again across the Paraná River in Argentina, special insofar for its protection against ship collision. We'll have a special lecture on that, and we can see here above water, that's on about 50-meter deep piles for a rather big ship to protect. Lately, 2004, until then, there was only one bridge across the Panama Canal, an old steel truss. New one required, so we did what we call normally in our house the second Panama Canal Bridge for Bilfingen-Berger, 330 meters, taking into account, of course, the widening of the Panama Canal, which takes currently place. So this is just a development of cable-stayed concrete bridges, and you've seen one can build them as light visually as steel bridges, if one dares. Now, I come to Riccardo Morandi's bridges. Riccardo Morandi was an outstanding Italian engineer, famous at his time, I think nearly forgotten today. I wonder whether you have ever heard of Riccardo Morandi. Probably not. And he did the first very massive, but they worked, cable-stayed concrete bridges, and I'm happy to recall his works. I mention again, his main thing was the the Maracaibo Bridge, but that comes under a series of concrete bridges, comes a little bit later. So this here, the Wadi Ghouf in, Libya. It was, I don't have a better picture. It is actually a double bridge. You see it below here, but I couldn't get a better one than this. And you see here Morandi's principle, heavy beam, single forestays and backstays, concrete stays, I call it, encased in concrete, so they're very strong. And in addition to stiff A-tower, he uses additional V-piers. So the heavy beam is supported here, and there's a drop-in girder in the middle. Today it sounds old-fashioned, but at that time he was a forerunner, state of the art. He made then the Rio Magdalena Bridge in South America. Similar way, concrete stays, but without the additional V-piers. But he never came around to use multi-stays. That was then after him. We have all other examples for what I call concrete stays, meaning for stays we use tendons, post-tensioning Spannglieder, but we encase them in concrete and post-tension them in such way that even under heaviest life load, there is no tension in the concrete, so it's all uncracked and it's very stiff. So what we have here is basically not what we consider today an elastically supporting cable stayed bridge, but we have a continuous girder who is nearly rigidly supported by these very stiff concrete stays. Can also be economic. We have here a Metten bridge. I think it's a Danube in South Germany, Metten, Danube River. Metten bridge. And in Frankfurt, Flößer bridge. We will have some details on its construction, because the construction, of course, is a little bit involved. If you have only one support here, how do you bridge these 100 meters? Means a lot of auxiliary equipment to build it. We will see that later. So that's a little shortcoming, but here there were certain architectural reasons. I also did an alternate which wasn't successful. This was done by Herbert Schambeck. He started as assistant, then chief engineer of Finsterwalder, and where Finsterwalder very often had the basic concept, Schambeck did it in detail. So he was the engineer for these and many other important major bridges. Free cantilevering was invented by him in detail, also an important German engineer, but second in command to Finsterwalder. Finsterwalder is always mentioned, Schambeck not so much. I know him well personally, he's an outstanding engineer. Now, we talked about massive single concrete stays, and these have been extended to walls, I call it for lack of better, and a famous example is the Ganter Bridge. What I call a concrete wall means we have here, we extend the length of support. These are, again, like in concrete stays, post-tensioning tendons, encased in concrete, very stiff. So I say instead of having concrete stays, these are stay walls. You can also say it's an extra dose bridge. It's hard to discuss. I just mention it here. So we have over a longer distance a stiff support. The Ganter Bridge is curved, and you can take the deviating forces with that. Quite involved, a famous bridge by Christian Menn, the most famous Swiss bridge engineer, who, by the way, was also kind enough to write a review on my book, and I had asked him. He made some famous bridges in Switzerland. Another concrete walls is the second Manama crossing at Bahrain, where I was checking engineer, and there these, you can call them, I call them walls, you can call them sails. They consist of individual precast beams with the holes for the post-tensioning in. So they were installed one after another. The tendon threaded in and the whole thing post-tensioned. Here the basic idea why to use that was corrosion protection for the stays, because there we have the hot climate, salt, water, the worst combination you can have. In my script I have it all in detail. So by encasing the steel tensile members in solid concrete, it's the best you can do in corrosion protection in a hot, aggressive salt atmosphere. It was in quite some detail, very nicely designed. You can see all these, say, circles are individual precast elements. They come down here, precast barriers. A very nicely designed bridge was done by Dar al-Handasa. Doesn't tell you much. Is an Arab consultant residing in London. Very nice bridge. Now, another development was to use as thin beams as possible. Now, in some lectures later, we will talk about how to design a cable-stayed bridge, and then we have the beam under high compression, and the buckling problem and all these things come up. On the other hand, the moments are restraint moments, and the amount of moments for a given load goes down. The more flexible the beam is, I'll show you all that in detail. So there is the idea, let's make very, very flexible beam. Of course, the limit is the buckling. But you can go down. I'll show you how to calculate these things. It's fairly, in basically, it's fairly simple. But that's the idea behind. The thinner a beam, the smaller the moments are. But if you go to 0, it will buckle out. So there is a there is a limit. And that was the investigation. There is a certain Professor Walter, who was long years assistant of Leonhard, was in Lausanne. And he built a small cable-stayed bridge at Diepholzau, that is the Rhine River, just before flowing into Lake Constance. Bodensee is Lake Constance. And he made then also tests with micro-concrete and found out, okay, we can do it. He had a thin, this is 1 in 180, something like that, which is not extraordinary. I showed you Helgeland is already 355. But okay, it's a solid, thin concrete beam. That is the new one. And Schleich then did it in earnest, Evripos Bridge in Greece. He also used a solid concrete beam, what is it, 45 centimeters thick, for a main span of 250 meters, which gives a slenderness of 1 in 440, which is the world record. And of course, this is simple to cast, and due to the elastic support of this solid slab, you have an extremely good distribution of single loads, meaning wheel loads. The wheel loads are distributed forwards, backwards, sidewards over many stays, over a long area of beam, and so you really can do it with these 45 centimeters. Naturally, the wind transversely is minimized. There's very little area of attack against the wind can blow. So it's a reasonable, it's a good system. I'm not sure whether to go very much further with the span, but it's a world slenderness record. Done by Jörg Schleich. I'm not sure you know him. He used to be a partner in Leonhard Andre and Partner. I worked with him in my early times at Leonhard. He then went on his own, founded his own consultancy, Schleich, Bergermann and Partner, in Stuttgart and Berlin. And his main task was, he was the engineer for the Olympic roof in Munich, which was completely new at the time. And that was his main thing as a younger engineer, and from then on he did all sorts of interesting things. Okay, now we can end up, as we did before, with the record spans. And now we have here, just to mention, the Maracaibo Bridge is a series, 7 bridges with about 250 meters, very early on. The Wadi Kuf, also Morandi, we have seen with nearly 300 meters. And now we start with the Breton Bridge, which I mentioned because it took away my world record from the Pesco-Kennewick Bridge. Now this is across the Seine River, early cable-stayed bridge by famous French contractors and one of the leading, at that time, French engineers, Jean Muller. I know him quite well because when I was working doing cable-stayed bridges in the US between 1975 and 1985, there were also always designed a steel and a concrete alternate. And it so happened he was busy there. He normally got the concrete alternate, and I had the steel alternate, meaning steel composite. And so once he was an excellent engineer and a very hard competitor because he really could thin out his bridges. And I know an important bridge, Sunshine Skyway, we will see later, I lost against him, although it was in the approaches we didn't do. But the next one, Baytown, a very major bridge, we won against him, so we were even. But we knew one another well because in Texas, during the early design phase, we sat both on the table there at the Texas Department of Highway, and there was a very fine old gentleman, Wayne Henneberger, was a state bridge engineer, and Jean Muller and I, we were fighting. Everybody tried to get some advantage for his design in the design conditions. So after 2 times, Wayne Henneberger said, "Well, gentlemen, I can't stand your fighting. From now on, we'll have separate meetings for concrete and for steel." But we held one another in high esteem. I considered him an outstanding engineer, and so we had a good personal relationship. Well, Breton was concrete design, central plane of cables tied here with post-tangent ties to the webs, built by free cantilevering, the inclined webs precast elements, the others cast in place. Something Jean Muller told me once he would never do again, either make it cast in place or do it precast. The mixture is no good, he said. And a nice bridge completed in 1977, I think I said across the Seine River in France, under Jean Muller. Then the next record came in Spain. There was planned a new lake by a dam to be built, and so it was rather unusual, long main span, short side spans, and so on. And the doyen of the Spanish engineers, Carlos Fernandez Casado, was in charge, and he was then Manterola and all these others which are famous today were his pupils. And there was a long consideration how to go about, and finally they came up with a world record, 440 meters. Now this is cast together with the abutment. You see the side spans are too short. And here we had special abutments, tie downs, anchorages, and so there is a joint in the middle because it's fixed to both abutments. We need some way of getting the temperature out, and there's this, which is unusual. There's a joint in the center, but given by the conditions, 440 meters was in Spain, the world record. Casado, and finally the record, and it is still there, went to Norway. It was at the same time when we did the Helgeland Bridge, much more north. We had a proposal in for this, but we couldn't get both of course. So the 530, the world record, current world record, was done here with a very nice wind, aerodynamically shaped cross-section, 530 meters, 8 hour, all the proper way done. Now, 530 meters in most countries of the world would have been built not in concrete, but in at least composite, meaning a steel grid with a concrete roadway slab, or all steel. Not in Norway. Norway, they know how to build concrete structures. They have, for example, of course, the world record for free cantilevering Horngirders with, I think, 302 meters. The Helgeland, which we did with 425, was the limit, of course, in concrete. And even the 530 meters, they do in concrete. That's why all these limits of spans I mentioned to you, they are relative depending on the country. Whereas in the US, they would probably start from 300, 350 with composite. They can't do orthotropic because they can't weld on site, so steel is out. They do steel composite, bolted steel with a concrete roadway slab. In Norway, they go easily 530, maybe even longer, in concrete, because they know all about concrete. Their contractors are used to that. It always depends on the location, so that when I give you limits, it's very, very general, depends on the country. So 530 meters is the world record in Norway. And that gave us a basic idea on the development of concrete cable-stayed bridges. I repeat what I said. A concrete compression member, the beam, is more economic than a steel compression member. On the other hand, it's heavier, costs more cable steel. And for short spans, the advantage of the easier carrying of the compression is governing, but the longer the span becomes, the more the additional cost for the cables take over, and at a certain limit, say 400 meters, the additional costs of the more cable steel are bigger than the savings in cost for the beam. That is the cutoff. And where this point lies, whether 400, 350, 530, depends very much on the country and the way the contractors work. Let me, at this place, use a word on towers, whether we build them in steel or in concrete. Basically, from today's view, we have the same situation. We have a mainly compression member. The bridge is hanging in there. Of course, by straining at the cables, we move the tower head and we get restraint moments. There are also moments in, but it's mainly compression. So, very generally speaking, a concrete tower is more economic than a steel tower. I do not use these reservations as I do for the concrete beam. I do not say up to 100 meters it's concrete and then it's steel or something, no. We have there always the compression governing little bending. So most of modern cable-stayed bridges will use concrete towers. There's only one limitation, and that is if we have very bad soils conditions. Maybe we need, say, 100-meter long piles because we have 80 meters of mud and then only some load-bearing strata. Then the additional costs, because of the higher weight of the concrete tower, the additional foundation cost may eat up the savings in the tower itself. You understand? It's not in the tower, but what it costs to bring it down. But this is rare, and so if you would go through again what we discussed today, then you'll find the early cable-stayed bridges. Say, they are steel cable-stayed bridges. They use steel towers. Steel contractors, they couldn't think of something like concrete for towers, no good. But it soon come out that also the steel bridges saw the advantage of concrete towers, and today all types of cable-stayed bridges use concrete towers, with the one exception that the soils condition must not be too bad. Well, thank you very much.